Hi, everyone. Let's talk about gases. Now, gases have been studied for a long time in chemistry, and we know quite a bit. What's really cool is that it doesn't matter which gas you're talking about. The theory applies to all gases, pretty much. And so let's start out, sorry, still in the manner of an introduction. Um, there's going to be a lot of theories here. So it may seem a little overwhelming, but by the end, I'm hoping that I can sort it out and make it much more clear for you. Okay, so what we're going to do is just see a whole bunch of theories dealing with gases, and we'll see how they're all connected together. And then finally, I'll show you a portion of the sample test where I give you all the equations. So you don't have to memorize this. You just need to understand it. You need to understand enough so you can choose the right equation to use to solve a given gas problem. Okay, so let's start here. First theory, it's called the kinetic molecular theory of gases. Okay, so what's this all about? It's actually pretty important. So you might see this in later chemistry classes, might even see this in physics. So what's the idea? Well, when we think about gases, if you zoom in, look at them, what is a gas? Well, what the first thing the theory says is that gases consist of large number of molecules or atoms. It might be helium gas, right? Helium atoms. It might be methane, CH4, carbon dioxide gas, CO2. So it's a large number of them. They're in continuous random motion. They're unstuck from their neighbors. They're just bouncing around in a volume, whatever. That's what we imagine a gas is. Just individualized molecules or atoms bouncing all over the place, never stopping. Second thing, if you compare the volume that the gas is occupying, like maybe this room is filled with air, and then you compare the size of the molecules, well, the size of the molecules are super, super tiny. And pretty much if you add up all the volume of the gas molecules in a room, in the air, all the molecules that make up the air, that occupies a very tiny fraction of the whole room. They don't take up much room. So that's our second part of this kinetic molecular theory. We're going to say the volume of all the molecules, you can just disregard it. Pretend the volume of the molecules are essentially zero. And that's compared to the whole volume of the room. Molecules are just super, super tiny. They don't count. They don't use up space. Now, honestly, that's not a true statement, but approximately, it's pretty darn close. Third assumption of the kinetic molecular theory of gases is that the gas molecules are in such fast motion, there's no time for them to attract or repel each other. In a previous video, we talked about intermolecular forces. So if you can slow down these gas molecules, then when they collide, they might tend to stick together through intermolecular forces. But at the speeds at which gas molecules typically are found, they're moving really, really fast. And they don't have time to attract each other or repel. They can collide off each other, but the collision is so high energy, it just bounces off, even if they were capable of sticking together through an intermolecular force. Okay, this one is also approximately true, not 100% true. In fact, it is not true at low temperatures. So if you take your gas and slow them down, okay, now as they're colliding, they're going to collide more softly. Now they have a chance when they collide, they might stick together through intermolecular forces and fall out of the gas phase and start liquefying, start condensing as a liquid. Okay, so if you go to low temperatures, then you don't have a gas anymore, and the kinetic molecular theory of gases fails. Okay, but at normal temperatures, they bounce around, they don't attract or repel. Also, it's not true at high pressures. So if you start squeezing the gas together, really, really, really pressurized, now you can squeeze the gas molecules so that they actually can see each other a significant amount of time. And now their intermolecular forces can start making them stick together. And now they're if the temperature is too high, they may not slow down enough to stick together permanently and settle out as a liquid. But if you pressurize them so that they actually are closer together for longer amounts of times, because they're so pressurized, so pushed together, well, now, because they're so close, their intermolecular forces can operate for a longer amount of time, and they do start attracting each other. Okay, so that's when this theory fails too. High pressures, extreme pressures, and very low temperatures. What are those numbers? Well, you have to tell me which gas we're talking about. If we're talking about steam, water vapor, then low temperature is anything under 100 degrees Celsius, right? Because then that's 100 degrees Celsius, water can change from a gas to a liquid. It can condense. But if we're talking about helium, you got to get pretty close to absolute zero before helium will condense into a liquid. Yeah, absolute zero is pretty darn low. So we'll just, we kind of have to be a little ambiguous. It depends on which gas molecules we're talking about, so that if we knew which gas, then we could have a better idea what low temperature and high pressure meant. Anyways, just want you to be aware that this is not a perfect theory. Okay, fourth idea. Energy can be transferred between molecules during collisions, right? Because the gas molecules are bouncing all over the place, willy-nilly all over the place. But the average kinetic energy of the molecules does not change with time. So the average. So in this room, there's a lot more than a mole of gas molecules. There's a lot of gas molecules. If you can measure all their kinetic energies, some of them are going really fast, others going kind of slow. Some of them just hit head on and now they're not going very fast. But on average, the average kinetic energy is the same, as long as I don't change the temperature of the room. And we kind of knew that from a previous video, right? We said that as temperature increases, so does molecular motion. Higher temperatures, molecules move faster. And so if we're keeping the room or your gas molecules same temperature, on average, they're moving them about the same at any point in time, the averages. What about that average? Well, it's actually true that the average kinetic energy of molecules is proportional to the Kelvin temperature. So higher temperature, more kinetic energy. Why do we have to use Kelvin? Well, because Celsius and Fahrenheit have negative temperatures. And what does it mean to have a negative kinetic energy? So we have to use the Kelvin temperatures so that all the temperatures are zero or a positive number. And then that makes sense. Yeah, kinetic energy is either zero, no kinetic energy, or it's a positive value. The higher the positive value, the faster the molecules move. Okay, so this is actually a key point too. When you're dealing with gases, we must use Kelvin for temperature. Otherwise, we're going to get bad numbers, especially if we use a negative Celsius or a negative Fahrenheit temperature. The math is just going to go, whoa, I can crank out a number, but it's not going to make any sense. So you got to use Kelvin. What comes out of the kinetic molecular theory is that gas molecules are super tiny, not taking up much space, and they're moving all the time. And so in fact, pressure is caused by collisions of the gas with the container. Collisions between gas molecules and the container. And so it's kind of nice to think about gases on a molecular level, because then this kind of makes sense. So if you have a balloon, I should have brought one. You blow up a balloon with air and the balloon expands. Well, why is the rubber balloon getting bigger? Well, as you put in more gas, more air into the balloon, they're bouncing around and they actually collide with the inner surface of the rubber balloon and push it outward. It makes it expand. And so the gas molecules are in constant motion. They're colliding with the rubber balloon and just making it expand as you put in more air molecules. Cool. What else do we need to know? I think we got it all. Good. Kinetic molecular theory of gases. All right, what else is going on? Oh, yes. When you talk about gases, we're going to talk about pressure. We can squeeze these gases under high pressure, and we can let them expand under low pressure. Pressure, pressure, pressure. We've stress. No, not that kind of pressure. These have been studied. Gas has been studied for a long time. We got a lot of gas laws, a lot of theories about them. The problem is we had a lot of different people studying gases, and they all had to deal with the pressure of the gas. So unfortunately, over time, no one decided on which unit was the best for pressure. So we got a whole bunch of them. You need to be aware of these different units of pressure so that if you see them, you know what they're talking about. I will do my best to stick to atmosphere as a unit for pressure in my class. But I'm assuming that you may take other science courses that deal with pressure. And so you will, in that case, see these others. And you maybe in everyday life, you may have seen these others. So the weight of the atmosphere on us at sea level is the pressure of the atmosphere. So that's one way to measure measure pressure is how's it compared to normal atmosphere. So 1 atm is one unit for measuring atmosphere. We can also use a barometer to measure air pressure, in which case we're looking at how much air pressure pushes up a column of mercury. And you measure the height of that column of mercury in millimeters. So one way to measure pressure is how high is that mercury rising with pressure. And 1 atmosphere pressure can push a column of mercury 760 millimeters high. Okay, I don't expect you to memorize it. I'm just saying, hey, millimeters of mercury is a unit for pressure. And someone said, mmHg, that's just too many. How about TORR? That's the number of letters. Anyways, a torr is equal to 1 millimeter of mercury. And yeah, there's a third unit for pressure, torr, that's exactly equal to a millimeter of mercury. Before the metric system, we were using inches. So inches of mercury. So the barometric pressure might be 29.9. That's 1 atmosphere pressure. If you watch the weather report, there's a high pressure cell coming in, a low pressure cell where the rain is coming. So we watch the barometric pressure and we can forecast when we have sunny weather and wet, rainy weather, snow, whatever. And sometimes they report the air pressure, barometric pressure in inches of mercury. And usually around 30 inches means high pressure and good weather. What about bicycle tires and inner tubes and tires on cars? Well, the pressure is being measured in pounds per square inch. Pounds per square inch, or PSI. So there's another unit. And 1 atmosphere is 14.7 pounds per square inch. Physicists have another unit called pascals. 1 atmosphere is 101,325 pascals. And a pascal is also called a bar. Okay, a pascal, 1 pascal equals 1 bar. I've seen that unit too. Anyway, whole bunch of units. Now you've seen them. I'm going to try and stick with atmospheres, although torr and millimeters of mercury is also quite common, especially in the medical field, right? If you're a nurse or a doctor and you want a patient to take some oxygen because they have some type of lung incapacitation or something, you're going to measure the pressure of the oxygen in millimeters of mercury, or torr. So there we go. Ooh, how about a demonstration about atmospheric pressure? So this will be fun. We don't have too many demonstrations in my classes, sorry. But I got one here for you. So this guy has got a big metal drum and he filled it up with water and he started heating it. Okay, so what has he got here? This guy's pulling out, looks like a big Bunsen burner. And I think there's another one over here and looks like there's a third one here. So just gas, flame, heating the bottom of this drum. And like I said, it was filled with water. And that you can see the steam coming out. Okay, you can see he's putting the cap back on the lid and closing it up. It's got a sealed container now. Oh, man. Whoa. Okay, then so my question for you is, what crushed that can? Some of you might be saying, oh, it was vacuum. And that's partially correct. I mean, that is one way to try and explain it. So way back at the start of the video, they were boiling water out of this container, right? So they filled up with, no, they didn't fill it, but they had some water in here and it was filled with air and they started heating it. So then the water boiled, became steam, vapor, water vapor. And so the liquid water changed to steam and started rising and it pushed out all the air out of the container. And you boil it for a while so that all the air comes out and it's filled with steam. And then he put the cap on it, right? So he's putting the cap on it. And now it's got a hot container of steam, no air inside anymore. It's all steam. And then where is he going to put the hose underneath? I think that's the key part. Go ahead. I love the scream. Oh man. Okay. Why did it get crushed? Well, as he cooled down the can, especially from the bottom, it cooled off the water in there, cooled off the water vapor to below 100 degrees Celsius, so that the steam turned back to liquid water. And then there's very little gas inside. Essentially, it is a vacuum or pretty low pressure. But what crushed it? Did the vacuum just suck in the sides? Some of you are saying, yeah, that's what happened. I saw it happen. Well, think about it on a molecular level. Let's zoom in, try to explain this. Okay, so let's talk about molecules and the kinetic molecular theory of gases. I'll go over here. There's some room. Okay, so we have this container. And it was filled with water vapor that turned into liquid water vapor. And so down inside here, you got a puddle of water, and now it's empty. So what do we see on the molecular level? Well, maybe one or two water vapor molecules flying around here. It's not completely empty, but most of the water vapor turns to liquid water and it's down here at the bottom. And then if you zoom in on the can, well, it's steel. And so you might see the iron. Steel is essentially iron with a little bit of carbon in it, stainless steel. So you could zoom in, you'd see little atoms of iron that make up the cannon. So what pulled it in? The little water molecules, a few of them yanked on the side of the can? No. What's outside? Air at 1 atmospheric pressure, and it's bouncing around all over the place, including bouncing off of this can. There's lots and 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 lots of gas molecules all colliding on this can, bouncing on it and creating pressure on the outside. And on the inside, there used to be air in there that could bounce and collide on the inside and keep the walls of the container from being crushed by the atmosphere. But not if you boil off the water, push all the air out, cool off the inside, and you take out all the gases. Well, now there's no pressure on the inside to resist the atmosphere from pushing in on the side of the can, and that's what collapsed it. That's pretty amazing that the air right now is pushing on us with the same force as it's pushing on that can. I know, take a deep breath, put more air inside you so the air inside you can push out and resist the external pressure on you. And of course, you got tissue and bone and fluids in there pushing out too. But the same pressure is on us right now, 14 pounds for every square inch. So on the back of your hand, you can draw a 1-inch square, and on that piece of skin is 14 pounds of pressure from the atmosphere. Cool and crazy at the same time. A little more respect for the atmosphere, huh? Okay, we saw our first theory, kinetic molecular theory of gases, and from that we saw that pressure is essentially due to collisions of gases on the container. Essentially enough pressure to collapse, condense, contract, smash that big steel drum. Here's a second theory. It's called the Ideal Gas Law Pvnr. Pvnr. Okay, and here's the idea. If you have an ideal gas, I should have mentioned that when we're talking about kinetic molecular theory. Okay, so for most gases, these rules are obeyed. Helium gas, carbon dioxide gas, methane gas, chlorine gas, whatever. It is true, for the most part, all those molecules are in fast motion, never stopping. The size of the molecules, totally so small compared to the total volume, you can just ignore the volume of the gas. The attractive repulsive forces don't operate because the molecules are moving so quickly, they don't have time to attract or repel each other. Energy is transferred during collision. Yep, pressure is caused by collision. Average kinetic energy is proportional to the Kelvin temperature. It's not true at low temperatures or at high pressure. So most of the time, doesn't matter what gas it is, helium, nitrogen, fluorine gas, whatever, they all behave the same, ideally. And if it's not ideal, like a low temperature or high pressure, then it's a non-ideal gas. And we can't really predict it as effectively as we did before. So an ideal gas obeys the kinetic molecular theory of gases. Okay, so we have an ideal gas. It's obeying the kinetic molecular theory of gases, which means the temperatures are not too low and the pressures are not too high. And then this equation, simple equation, can do a whole bunch of predictions accurately for a whole bunch of gas molecules: helium, argon, neon gas, methane, carbon dioxide, whatever. It all works as long as you're not at low temperatures or high pressures. P stands for pressure, V stands for volume. Pressure, I'm going to stick with atmospheres as my unit. Volume, I'm going to choose liters. Number of moles, well, I'm going to stick with moles as a unit. So how many gas molecules do we have in moles? And then temperature, oh, we already said, it's got to be in Kelvin. Exclamation point. We can get into trouble and get wrong answers if we don't have Kelvin. R, that's a conversion factor. It's called the gas constant, sometimes called the universal gas universal gas constant, because universally it applies to anything in the universe, as long as it's not at too low of a temperature, too high a pressure, any gas. And the conversion factor that converts this side, atmospheres and liters, with this side, Kelvin and moles, is something you don't have to memorize, but I use it so much, it's stuck in here. It's 0.0821. And then to memorize the units, you don't have to, just memorize Pvnr. which actually you don't have to do either. I'm going to give that equation to you as well. But what are the units? Well, I want to cancel out the T and the N. I need to cancel out the moles and the Kelvin. And what do I want this number to change into? Units of this side, atmosphere and liters. So there's 4 units here. It's just a crazy conversion factor. Don't worry about too much. What you need to worry about is finding it, which you'll find at the top of the exam or sample test. Know how to use it. P is going to be atmospheres, volume is going to be liters, N is moles, T is Kelvin. How will you remember all that? I will give you R and just look at the units. So here's the universal gas constant. And in order for this equation to work and give you right numbers, you have to have atmospheres, liters, moles, and Kelvin. Atmospheres for the pressure, liters for the volume, moles for moles, and Kelvin for the temperature. Nice. What else do I need to say about ideal gas law? Nothing else. Cool. Okay, this is a latecomer. Like I said, chemists, scientists have been studying gases for years and years and years. This ideal gas law came later in that study. What came before? Well, a whole bunch of other gas laws. This is the ideal gas law. Ideally, you should be using this one. But there are some older gas laws that actually are still pretty useful. So on Canvas, you're going to find a handout. You don't have to memorize it. It's just there to help us understand. And it's this handout right here. And I just got some cool pictures to try and explain each of these other gas laws. And let's just go through them and just understand them, not memorize them. Okay, well, there's something called Boyle's law. Don't remember his first name, but Dr. Boyle published this, and he's been famous with this equation ever since. P1V1 equals P2V2. What does that mean? The ones mean the first state of the first situation. Twos mean the second state, the second situation. Okay, so let's suppose we have this cool canister made of metal, and we have this metallic lid, and it's greased, so it can slide up and down. But it's a tight fit, so the gas can't slip out, can't leak out. Fill the bottom part with gas, and this lid, well, let's say we have to put a weight on top of it to keep the gas under pressure. How come this lid and the weight don't fall down? Well, because the gas molecules, by the kinetic molecular theory, are in constant motion, and they're constantly colliding with the bottom. And their collisions keeps the lid from falling. That's the source of pressure. It's pressurized and pushing the lid back up. Okay, so now measure your pressure. And you got a pressure gauge, I guess, and measure. Oh, I can't write on that. Now I can. Okay, so measure the pressure. And I don't know, let's say it's 10 atmospheres. I'm just making up stuff. And the volume, we'll measure the volume of the container. Let's say that's also 10 liters. Making up stuff. And then that's the first situation. And then we're going to change this container so it looks like this. Add a second weight. And with 2 weights on here, there's an increase in pressure. It's going to squeeze this down. And so now we have a new pressure. Let's say it's now 20. So what's the new volume? Well, this equation will tell it for you. The first pressure is 10 atmospheres. The first volume is 10 liters. The second pressure is 20 atmospheres. And V2, the second volume, is what I want to know. The volume in the second situation. Divide both sides by 20, and 10 divide, so I should just do it, sorry. 10 liters, and we're going to divide both sides by 20 atmospheres, so that equals V2, right? So divide both sides by 20 ATMs, and the 20 ATMs will cancel out here. And then these 2 units cancel out. So you got 10 over 20, which is 1/2. 1/2 of 10 is 5 liters. Cool. Boyle's law does a great job of predicting the missing component, missing property. If you have 3 of these, the pressure, volume, first pressure, first volume, or the second pressure, second volume, if you have 3 of those, you can calculate the missing one. So Boyle's law is cool. More importantly, Boyle's law is saying that as you increase the pressure, the volume decreases, right? And hopefully that makes sense. Squeezing on this container makes the pressure go up from 10 to 20, but the volume was cut in half. It shrunk from 10 liters down to 5. They're opposites, inversely proportional. P went up, but V goes down. And then let's get out of the pen mode. I think there's an example of the real world. Yeah, here we go. Oh, I should clear the screen, sorry. There we go. Scuba divers, if you watch the bubbles rise up as you exhale deep down the water pressure is really high and your air bubbles will be very small because they're under large water pressure being squeezed. But as the air bubbles rise up, the water pressure gets less and less, pressure gets less and less, which means the gas volume will increase and the bubbles will expand as they rise. That's cool. Boyle's law in action. Charles' law. Okay, Charles said, let's get that container, Boyle. I'll put 2 weights on there. That's how you left it. And I'm not going to change the weight of the container. I'm not going to increase the pressure or anything. I'm going to heat it up. So you heat it up, and what happens? You see the volume goes up. So more temperature, more volume. The volume is actually proportional to temperature. Cool. His equation is V1 divided by T1. So it was easy for me to type this in, but really it's a fraction. Well, it is a fraction. It's volume divided by temperature. It might be easier for us to write it this way. It's the same equation. Cool. You have to use Kelvin. You must. Especially if you have negative Celsius. Yikes. Then you might calculate a negative volume. What does a negative volume even mean? Yeah, don't even go there. Make sure you use the Kelvin temperature. So this equation will give you correct answers. But the main idea of Charles' law is that as you increase the temperature, the volume increases. If you lower the temperature, the volume decreases. And a real life example is right here. So in this Petri dish, this big evaporating dish, glass container, it's all frosted over because this Dewar flask, this big thermos bottle, contains liquefied air, liquid nitrogen. Okay, so you got to cool and pressurize air, nitrogen gas. Sorry, now air is essentially what, 76% nitrogen gas? So cool it down and pressurize it, force it to be a liquid. It's super, super cold. And it's sitting in here and it's fuming because it's warming up and changing from liquid to gas. Anyways, we got a normal rubber balloon here and we stick it into the liquid nitrogen to cool it down, and you can see the balloon shrink. If you pull this out and put it on the counter, it should reinflate as the gas warms up and starts putting more pressure on the balloon and expands it. So right now, as it cools down, the gas molecules move slower, they collide with less force, and the elastic balloon contracts. If you heat them up, the gas molecules move faster, push harder on the inside of the balloon, and expand it. Charles' law. Volume is proportional to temperature. Avogadro's law. I've heard that name before. Avogadro's number. Yeah, that's how we define a mole. So Avogadro also worked with gases. So he has a law that says, hey, Charles and Boyle, can I borrow that container again? Yeah, so I got your gas in here with 1 weight on there. What if I pump in more gas molecules, increase the number of moles of gas, then the volume increases. Yeah, and the equation there is V1 divided by N1 is equal to V2 divided by N2. That's the equation. As long as you know 3 of these numbers, you can find the missing one. And the real life example is like that flat tire. As long as you patch the hole, pump in more air molecules, the volume will increase. It'll reform the shape of the tire. It also helps us breathe. So as your diaphragm lowers, your rib cage will expand and the volume of your lungs will increase. And that actually will draw in. Does it draw in? No. The air pressure outside is pushing more air into your lungs. There's a lot of pressure out here, but you expand your lungs, increase the volume, and in goes more air being forced in there by the atmosphere. Cool. Avogadro's law, another gas law. Gay-Lussac's law. Okay, Gay-Lussac wanted to get famous too. So he was like, Boyle, okay, you talked about pressure and volume being related. Charles, you did volume and temperature. Okay, got that. More temperature, higher volume, higher pressure, smaller volume. Okay, what else we got? Avogadro, volume and moles. Come on, you're killing me. All these different variations. What's left? What hasn't been talked about yet? How about pressure and temperature? All right, Gay-Lussac, good job. We got your name in the books. So now you can't change the volume, but you can change the pressure. So as you heat this container, Charles' law says the volume wants to increase. But as you're heating it, throw in more weight and try to keep the volume the same. Because also as you increase the temperature, the pressure is increasing. And so you're gonna need more weight to hold the lid in place. And how do we explain that? The kinetic molecular theory of gases. What is temperature due to these gas molecules? It makes them go faster. So you see the little, these little lines trying to indicate motion. This one's going to the right. This one's going down. So look at the length of that. Once you heat them up, the lines are longer, meaning it's a blur moving faster. Yeah, that's a good analogy. As you increase the temperature, gas molecules move faster. And when they collide with the lid, they'll hit it harder. And that means more pressure. Pressure increases as you increase the temperature. P1 divided by T2, P1 divided by T1 will equal the pressure in the second container divided by the temperature in the second container. Examples of this, well, this one's kind of boring. Can't change the volume. So I Googled this and someone said, well, this tire is at 20 PSI and the air is in the tire inside, the air inside is cold. And now it's warm, maybe at 32 PSI. I have to take your word for it because the volume's not changing. I can't tell. Here's another example of Gay-Lussac's law. Popcorn kernels, Jiffy Pop over here. Over here, Jiffy Pop popcorn. So we have a kernel of cold corn, put it in the fire. You have a kernel of hot corn. There's a small amount of small amount of water in there that can vaporize. And as you heat it up, the pressure of the water vapor, the steam, will increase until it explodes the corn kernel inside out, and you have popcorn. Of course, as soon as the shell, the kernel of the corn cracks and everything comes out, it's not Gay-Lussac's law anymore because the volume's changing. Now we're back to Charles' law, right? Yeah, volume increases with temperature. Here in the middle, sorry, I missed this one, is a pressure cooker. Now that's actually quite useful. In high school, I worked at Taco Bell, and I still like refried beans. So at home, I'll put them on the stove. They have to cook for hours in a pot of water that can't get any hotter than 100 degrees Celsius boiling water. So you have to wait a few hours for beans to cook. Well, at Taco Bell, we had this huge container, lots of them, and you could seal the lid. You could increase the pressure. And if you increase the pressure of the steam, the temperature will increase. And so now you can get the water hotter than 100 degrees. You can get up to like 130, 140. And if the temperature's hotter, the beans will cook faster. So a pressure cooker is actually pretty cool. get your beans cooked very quickly. But you got to be careful here, right? This is steam at 130 degrees, 140 degrees Celsius above boiling point. Ooh, don't let this crack or rupture. It's under high pressure. It's going to blow very hot steam and burn somebody. Okay, so if you have a pressure cooker, be very careful with it. Watch for any cracks in your container. Ooh, Dalton's Law, another video. We've seen a whole bunch of equations, whole bunch of laws. You do not have to memorize them. You just need to know what they do. Cool. What else do we got? Let's go back to this one. Okay, so we've seen a bunch of gas laws. Yay. They're going to come back. We're not done with them. Last topic before we do some sample problems, I think. Molar volume. I always look at this and smile. It sounds like a dentist is talking about the size of a tooth, the molar in the back of your mouth. Oh, sorry, bad dad joke. Okay, we're actually our chemists here. We're talking about molarity, talking about moles per liter, maybe. That's a volume. Okay, someone then said, we're studying all these gases, and Avogadro came in with a mole of gas molecules, and I can't see these gas molecules. Just how tiny are they? More to the point, why don't you show me a container with exactly 1 mole of gases? Maybe 3 sig figs worth of accuracy. And if I saw the container and I knew that it has 6.022 times 10 to the 23rd gas molecules in there, and there was a huge container, then I'd say, oh, maybe the molecules are pretty huge. If it was a tiny container, it's like, oh my goodness, such a huge number of gas molecules in this tiny space. I'd start to get a feel for the size of these molecules. So what container holds a mole of gas? Well, let's go grab PV equals nRT. And then you want to know what the V is? Yep. And you're telling me it's 1 mole? Yep. What's R? Well, go look it up. It's 0.0821, and we'll drop the units. That's safe to do as long as you know you're going to put all the other numbers in their standard units. Pressure in atmosphere, volume in liters, moles in moles. R, that's given, and temperature, Kelvin. Okay. That's my next question. Well, what temperature are you talking about? Because Charles' law says if you lower the temperature, you lower the volume. If you raise the temperature, you increase the volume. So I need to know what temperature. And so, the scientists thought about it a little bit. So I said, oh, if you're going to pick a temperature, let's pick a pressure too. Because which one was it? Boyle's law. If you increase the pressure, you shrink the volume. If you decrease the pressure, the volume expands. So you can pretty much have any volume you want, depending on how you choose the pressure and the temperature. Scientists are like, okay, wait. Let's not let this get out of hand. Let's do just something normal, like pressure. What's normal? 1 atmosphere. So everyone, let's go to the beach. Go to sea level, and we're going to choose the pressure to be 1 atmosphere. Yeah, good idea. I'll bring my boogie board and my surfboard, do a little research there too. What about the temperature? Well, it's a nice sunny day at the beach. Yeah, but it might be cloudy or windy. We really should be doing this in the lab, not the beach, guys. We'll build a lab at the beach and do it there. Okay, what's a temperature that's really stable that we can hold the temperature at so we can measure the volume pretty accurately? How about ice temperature? Yeah, we'll put our container, the balloon maybe, in a bucket of ice water. And as long as there's ice melting, we know the temperature stays constant. So that's what they did. They said, we're going to choose the temperature to be 0 degrees Celsius. And someone got hit in the back of the head. You can't use Celsius in the gas laws. Oh, right. Convert to Kelvin. What's the conversion equation? You don't have to remember this. I'll give it to you. But the Kelvin temperature is the Celsius temperature plus 273. So 273 Kelvin. And someone said, hey, we ought to do this more often. Well, what do you mean? Well, anytime we want to measure gases and we have to choose things, let's always choose these. This will be the standard way to do an experiment with gases. So these are our standard temperature and pressure. Cool. So whenever we study gases, let's always use the standard temperature and pressure. What's the standard temperature? Let's always use gases at STP. Okay, so I am going to ask you to memorize this. If you see a question on the exam says, you have a gas at STP. What? The P stands for 1 atmosphere. The T stands for 0. So just remember 1 and 0. But also remember, convert 0 Celsius to 273 using this equation, which will be given to you. Or just memorize standard temperature and pressure. STP is 1 atmosphere and 273 Kelvin. I'll need you to memorize that. Otherwise, you're going to have a hard time answering the question correctly if you don't know what the pressure is and the temperature is at STP. Ooh, we picked it though. Temperature is at 273 Kelvin, and the pressure is 1. Oh, I like that. I dropped all the units because they all match, right? We got moles, we got atmospheres, we got Kelvin. R has all those units too, and we're going to get our answer in volume. Sorry, in liters. Well, 1 times V is still V. So all you have to do is multiply 1 times 0.08 times 273, and the answer is 22.4 liters. That's the volume for 1 mole of gas at STP, standard temperature and pressure. That is the molar volume. So go find a box or a container, a balloon that can hold 22.4 liters, and there you go. That will contain 1 mole of gas, whatever gas you want. So I did find an image of that somewhere. Let's zoom out and find it. Oh, it's probably down below. Oh no, it's gone. I did not save it here. Thought I did. It's over here. I hope. There she is. Here she is. Okay. So we have someone holding a box that has been measured to be 22.4 liters. She should be wearing a jacket because at standard temperature, this is ice temperature, it's cold in the room. Anyways, that's the idea. 22.4 liters, standard temperature and pressure, 0 degrees Celsius, 1 atmosphere. That box holds 1 liter of gas. Well, the room looks warmer than 0 degrees, so cool it down to 0, and then it holds 1 mole of gas. 6.022 times 10 to the 23rd molecules of gas. This is actually kind of cool. Remember how we talked about liquid nitrogen? Nitrogen might be represented here, 2 N's triple bonded together. That's a nitrogen molecule, N2 molecule. Well, if you squeeze them together, cool them down, you can liquefy it. And 1 mole of nitrogen liquid only takes about 35 milliliters. I don't know if you can read the marking on this beaker. It's 40. That's a pretty small beaker, about this size. So 1 mole of nitrogen molecules in the liquid form can fill a volume of 35 milliliters. Warm them up, they expand to fill the whole box. That's cool. So you can get Avogadro's number of molecules, huge number, squeezed into 35 milliliters. Little container here. Now that gives you a sense of how tiny these molecules must be to have such a huge number in a small volume. Hope that's helpful. That's kind of impressive. Okay, let's do some sample problems. Let's alleviate any worry because we have to deal with all these equations. What kind of problems are you going to give us, Dennis, on the test? Well, that's what the sample test is for, to give you a sense of what you need to be able to do. Okay, you don't have to memorize. So Deep breath. We can do this. First of all, there's a lot of gas laws, so there are a lot of equations. And it isn't only, the next test is not only about gases, it's also about solids and liquids. So in the previous video, we did talk about changing the temperature and measuring how much heat it takes to change the temperature of a solid, liquid, or gas. If you want to vaporize it, there's the heat equation. And if you want to melt it or fuse the liquid back to a solid, here's that equation. And then right here, this middle two rows are the gases. I should say gas laws. And gas information, here's R, you didn't have to memorize that. At the top, we have the conversion to Kelvin, sweet. Avogadro's number, why did I leave off the 2? Whatever. We'll get into this equation and that one later in another video, and these other two. Got a couple videos yet to come. Let's just focus on the middle two rows here. We got PV equals nRT, ideal gas law. Got R for the ideal gas law. This one happens to be Boyle's law. This one is Avogadro's with moles. Here's Charles' law with temperature and volume. Gay Lessig here, he's in there too. And then we have something called the combined gas law. I guess we forgot who actually put this together, but it combined a couple of these gas laws to get this one. 1, 2, 3, 4, 5, 6 equations to talk about gases. How are we going to know which one to use? It isn't too bad. Here's the plan. Let's figure it out through doing a couple sample problems. I got 3 of them. 2 of them are shown here. Sample problem number 1, sample problem number 2. Number 1, hey, what's the temperature of 3 moles of argon at 20 atmospheres and 5 liters? I don't know. And the second one, suppose methane, I should have subscripted this, occupies 3 liters at 2 atmospheres. What's the volume? Wait, I thought you just told me it was 3 liters. No. What's the volume when the pressure is now 10 atmospheres at the same temperature? Oh, tell me the pressure changed? Yup. The first pressure, P1, was 2. The second pressure is P2. What about the volume? Well, that's what I want you to find. When the pressure is 10, the second time, tell me what the volume is in the second time, second case. For the first case, the volume starts at 3. Nice. So go find an equation with P1, V1, V2, P2. It's right here. And yes, that's all you have to do. Well, you have to do the math. So P1 times V1 equals P2 times V2. And P1 is 2 atmospheres. V1 is 3 liters. P2 is 10 atmospheres. I don't know why I'm crowding at the bottom of the page. Let's get some more room. And then V2 is, I don't know. That's my variable X. Divide both sides by 10 atmospheres. Atmospheres cancel it out. That's good because volume has units of liters. 10 atmospheres cancels out 10 atmospheres, so I just have V2 on the right side. And now what do I have? I have 2 times 3 is 6. Divided by 10, so there's 6/10 of a liter. That's 0.6 liters. You can use a calculator if you want to. Whoa, that's it? Yeah, that's it. Nice. What about the first one? Let's follow the same strategy. What's the temperature? There it is. We'll just call it T. 3 moles, so N equals 3 moles. Argon, I don't care. It's an ideal gas law we're using. These gas laws apply to all the gases. We didn't look at methane either. It's a distractor. In the real world, you have to identify your gas, but it's not going to change the chemistry or the math. 20 atmospheres, what's that measuring? Pressure. 5 liters is volume. What else is happening? Is it changing? No, it's not. There's no 1s and 2s. No 1s and 2s, it's just constant. Well, it's not really constant, but I guess it kind of is. What's the temperature when you have 3 moles, 20 atmospheres, 5 liters? There's no ones and twos. Which equation doesn't have ones and twos? This one, the ideal gas law. And that's the one you want. PV equals nRT. So P is 20. And then we're going to take the shortcut. I got P in atmospheres, V in liters, N in moles, and R is right here. Liters, good, that matches my liters. Atmosphere, good, that matches my atmosphere. Kelvin, ooh, that's going to be my temperature. Remember, it's in Kelvin. And moles, yeah, that matches the moles. So now you can just drop all the units. We know they're going to cancel out. They're going to take care of themselves. So pressure is 20, volume is 5, N is 3, R is 0.0821, and T is T. That's what we're trying to find. So scroll over to the right. Not too far because there's the other sample problem. Doing the math, 5 times 20 is 100. 3 times that number is, well, I might be able to do it in my head. Let's see, it's a 3, 6, 24. Yeah, times T. Divide by that number. I hope I did it right. I'm doubting myself. Correct me in the discussion for this week. And then I did it earlier. I got my calculator out, and there it is. I got a number of 406. It's rounded off to 3 sig figs, although maybe only 1. Yeah, just leaving 3. What are the units? This is temperature. It must be Kelvin. Is that hot or cold? Well, ice temperature is 0 Celsius or 273 Kelvin. Okay, so 406 well above 273. This is pretty hot. Oh wow, so this gas, argon, 3 moles, pressurized at 20 atmospheres in a 5-liter container. It's heated up to 406 Kelvin. Pretty hot. Hey, but that wasn't too bad, was it? So that's your strategy. For the gas law questions, label the variables, temperature, the moles as N. If in the question they say, hey, you have 3 moles, and later you have 20 moles, well, then this will be a N1. You started with, first case, 3 moles, and later N2 became 20 or something like that. Yeah, so if you see a change, use the 1s and 2s, and then just see what you have. Here I had a V and a P. 1s and 2s on the P and V, so they help me identify the equation. There you go. So just be careful and just label your numbers and you'll be fine. Let's see what else we got. This is combining a bunch of things. I got STP in here. We talked about that. You got Celsius. Why? We have to use Kelvin. So a bunch of stuff in here. Let me check down below. I'm wondering if this is the last one. Yes, good. All right, last problem. A 2.5 liter. Well, what is this? That's volume. I don't know if it's a V1 or V2 yet. Let's wait. Volume is 2.5 liters of a helium balloon is released at STP. What's the T and the P stand for? P is 1 atmosphere, and T is 0 Celsius. So if you put a 0 in here for Celsius and add 273, then the Kelvin is 273. So you get these equations on the exam. So the temperature is 273 Kelvin. It rises up until the temperature is negative 36 Celsius. Wait, I thought the temperature was 273 Kelvin. Well, it was at ground level when we were releasing the balloon. So the first pressure is 1 atmosphere, the first temperature is 273, and the first volume was 2.5. The new temperature, the second time, the second situation, it's negative 36 Celsius. So go grab that equation the Celsius temperature plus 273 will give me the Kelvin temperature. So we're going to add or subtract 36 and 273. And didn't I do that one? Yes, maybe. 237, hope that's right. Kelvin is T2 in Kelvin. And its volume, the new volume, the second volume, is 5.7 liters. What's the pressure? The second pressure. Cool. All right, what do we got? We got a V1, a P1, a T1, and a T2, a V2, and a P2. We got 3 variables with 1s and 2s. 3 variables with 1s and 2s. 3 variables, ooh, here it is. 3 variables with 1s and 2s. That's the equation we want. This is P times V divided by T. So we need to copy that a little carefully. I'll leave it on the screen so I do it right. I'm going to rewrite it so it's a little more clear. It's P1 times V1 divided by T1. That slash means divide. P2, V2 divided by T2. Nice. Okay, that's my equation. I get partial credit for showing that. If I keep cranking out the right numbers, then I'll get more credit. Yeah, so if this is a workout, show your work type of exam question, then yeah, definitely show some work. Ooh, I'll give you credit for showing me the equation and the correct conversion from Celsius to Kelvin. All right, so keep on working. What's my P1? It's the STP value. It's 1 atmosphere. Can we take the shortcut? Let's check. Pressure is atmosphere here, and we'll just make sure that the pressure ends up in atmosphere. Temperature's in Kelvin, and it ends up in Kelvin. Good. The volume's in liters, it started in liters. Good. Okay, the units will take care of themselves. They'll cancel out, and we'll be left with pressure in atmospheres. Nice. So check that you didn't have to convert anything else. Maybe a homework problem might put one of these volumes in milliliters. And remember then that 1,000 milliliters equals 1 liter. So you might have to do that conversion in a homework problem. But usually we don't measure temperature in Kelvin. We should if we're dealing with gases. So this will be a common conversion on the homework and in exams. You'll probably have to convert Celsius to Kelvin. And you'll get credit for doing it. All right, we dropped the units because they all match. What's my P1? Right up here, 1 atmosphere, so I just put a 1. V1, 2.5. T1, it's right here, 273. What's my P2? Well, that's what I want. You can make it X if you like doing algebra with X's. I'm gonna leave it P2. What's my V2? That's right here, 5.7. T2, over here, the one I converted, 237. Gotta be a little careful. These are so close. That's all the work I did. I had a physics teacher once who said the proper way to do algebra in physics is to solve for the unknown variable and then insert the numbers. Okay, so we could do it that way. That's actually how I did in my notes. So you could take this and say, I want P2 all by itself. So I need to multiply by T2 over V2, both sides. So then over here, the T2s cancel, the P2s cancel, leaving P by itself. Personally, I don't see the difference. You're gonna have to get P2 by itself by multiplying by 237 and dividing by 5.2 to get them to cancel out. Or you can just get a calculator, take 5.2 divided by 237 and get a number, and divide both sides by that number. Anyways, check my math, see if you come up with a pressure of 0.38 atmospheres. That's what I got. And that's enough for now. I'll see you in the next video.